Hi, my name is Tyler Lisowski, and I am presenting with Kodie Glosser. Today, we will illustrate how etcd operator automates etcd database management and eliminates database downtime. Etcd is the primary data store of Kubernetes and holds all the Kubernetes cluster state. Internally at IBM, our first etcd deployment model for kube clusters consisted of deploying and managing etcd instances on VMs using Ansible. As we scaled the number of Kubernetes clusters we managed, this deployment model became a bottleneck to the scale we could operate at due to the amount of engineering hours it took to maintain this automation suite at scale. Have any of y'all had the experience of going away for vacation for a week and coming back to an inbox of 1,000 plus emails that you have to process and respond to? That's the same feeling our engineers were experiencing as the various database creation and administration tasks queued up on a weekly basis. In addition, deployment and upgrade times of etcd clusters took on average 1 to 2 hours to complete, which increased the total time it took to get a Kubernetes environment functional. We needed to re-architect the way we executed etcd cluster deployments in order to scale the amount of Kubernetes clusters we could manage. Moving to an etcd deployment model centered around etcd operator allowed us to eliminate these bottlenecks. To put it in perspective, we manage 1,000 times more etcd clusters with our etcd operator-based solution than our Ansible-based solution. In addition, over the past year, we have spent significantly less engineering hours maintaining all etcd clusters managed by etcd operator compared to those managed by our Ansible-based solution. Now, let's illustrate the power of etcd operator by walking through a live demo of the etcd cluster deployment process. A quick note for those that have downloaded this slide deck. The number in the top left-hand corner of my screen corresponds to the slide number that has the content we are currently covering and will be updated throughout the demo. We are going to create a 3-node, highly available multi-AZ etcd cluster managed by etcd operator. We first need to define the database that etcd operator is going to create for us in a language it understands. That language is the etcd cluster custom resource definition. The CRD provides etcd operator with structured data that outlines all the requirements for the etcd cluster, which allows etcd operator to take action toward creating a cluster that meets all those requirements. The process is conceptually similar to that of an engineer working a GitHub issue that outlines the requirements for creating a 3-node etcd cluster. I have an example of that here. Once the engineer has read the requirements, he or she will begin executing actions toward achieving the desired result, like provisioning 3 VMs, and then installing and configuring etcd on each individual VM to create a functioning cluster. The engineer will provide status updates in the issue that will track their progress on the task and ultimately close the issue when the task is completed. The GitHub issue is the same idea as the etcd cluster CRD, and the engineer is the etcd operator. For all the non-engineers in the room, think of a person gathering 3 items in a grocery list at the grocery store. The person is going to read the piece of paper outlining the items and take 3 discrete actions that consist of finding each item and placing it in the cart. The grocery list is the structured data in this situation, and the person gathering the items is the operator. The key point in these analogies is enough information needs to be communicated to the operator in order for he or she to properly deliver the result. A lot of the same data you saw in the GitHub issue that the engineer worked is going to appear in the etcd cluster CRD resource. There's a few major sections of the etcd CRD to highlight. First is the size and version fields, which are going to control the size and version that the etcd cluster is deployed with. The next section are the scheduling rules, which are going to build upon kube scheduling logic to ensure the pods that run individual etcd instances end up on 3 different nodes in 3 different availability zones. Lastly, there are customizations to the configuration of individual etcd instances, including the supported cipher suites. We are going to apply this etcd cluster custom resource definition into the cluster, which etcd operator will then read to execute and create the database. etcd operator will execute the following series of logic loops after it detects the creation of the CRD. In the first logic loop, etcd operator has been told to create a cluster of 3 etcd instances at version 3.4.2 and currently has no existing instances. etcd operator will create 1 etcd instance to initialize the cluster and give it time to get healthy. etcd operator will also update the CRD to reflect what it has accomplished so far. Now, the next logic loop starts. etcd operator has been told to create a cluster of 3 etcd instances at version 3.4.2 and has 1 healthy instance. etcd operator will call into the etcd cluster and configure it to add a new member. Then it will spin up an etcd instance that will function as that member and give the cluster time to stabilize. Now, the final logic loop starts that will execute an action. etcd operator has been told to create an etcd cluster of 3 etcd instances at version 3.4.2 and has 2 healthy instances. etcd operator will call into the etcd cluster and configure it to add a new member. Then it will spin up an etcd instance that will function as that member and give the cluster time to stabilize. Finally, etcd operator has been told to create a cluster of 3 etcd instances at version 3.4.2 and has 3 healthy instances. Its work is finished, and now it takes some much needed time off, puts on a VR headset, and watches the tulips in Amsterdam safely from its home. At this point, we have accomplished our goal of creating a functioning multi-Z etcd cluster that is ready to serve requests. In this theoretical situation, the cluster is put into production use and results in downtime if it goes down. The cluster is also under strict compliance guidelines that the organization managing it has to meet. Security vulnerabilities can be disclosed at any time that impact the etcd version we are currently running. This is just one of the many reasons why we need to have a system that automates the entire etcd cluster upgrade process without any downtime. etcd operator makes this process as simple as one command: an update to the version field in the etcd cluster CRD resource. After we apply this change into our environment, etcd operator will detect that on the next reconciliation loop to begin the upgrade process. The upgrade process will consist of the following logic loops. In the first logic loop, etcd operator has been told to create a cluster of 3 etcd instances at version 3.4.3 and has 3 healthy instances running 3.4.2. etcd operator will patch the image of 1 etcd instance to be 3.4.3 and then give the cluster time to stabilize. The execution of this logic loop can be identified when a pod in the etcd cluster registers a restart. The execution of the next logic loop can be identified by the restarts of 2 etcd pods. In this loop, etcd operator has been told to create a cluster of 3 etcd instances at version 343 and has 3 healthy instances, 2 running 342 and 1 running 343. etcd operator will patch the image of one etcd instance to be 343 and then give the cluster time to stabilize. The execution of the final logic loop that executes an action can be identified by the restarts of 3 etcd pods. etcd operator has been told to create a cluster of 3 etcd instances at version 343. It has 3 healthy instances, 1 running 342 and 2 running 343. etcd operator will patch the image of one of the etcd instances to be 343 and then give the cluster time to get fully healthy. At this point, the cluster is fully healthy since all the pods are in 2 of 2 ready state, and we have completed the upgrade process. You'll note throughout the entire upgrade process, we had 2 pods ready to serve traffic at any given time, which ensures writes and reads can be processed throughout the entire upgrade. To recap, we were able to set up a HA multi-AZ etcd cluster in under 4 minutes and execute an entire database upgrade with 0 downtime in under 4 minutes as well. Now I'll turn it over to Kodie to take us through the power etcd operator can provide in disaster scenarios.
Thank you, Tyler. My name is Kodie Glosser. The next thing I'm going to talk about is what makes etcd highly available and go through a few different disaster recovery scenarios. As Tyler pointed out before, the etcd cluster custom resource definition has pod affinity rules that prevent pods from being scheduled into the same zone and host based off the node labels. As you can see in the image here, the pod affinity rules look at a topology key that specifies the zone. Let's go through a few different scenarios to help visualize high availability. In this scenario, our etcd cluster pods are scheduled across 3 zones, DAL 10, DAL 12, and DAL 13. Each zone has 4 worker nodes. Now let's say we have a power outage and we lose nodes in DAL 10, including the node that the etcd cluster pod was running on. The etcd operator will detect that the pod is dead and the actual peers does not equal the desired peers, so it will attempt to schedule a pod. It will look for a running and ready node in DAL 10 to be able to schedule to. As you can see in this example, the new pod came up on worker 1 in DAL 10. Now let us do the same scenario interacting directly with a Kubernetes cluster. As you can see here, I have the same setup with 4 nodes in DAL 12, 4 in DAL 13, and 4 in DAL 10. Additionally, you can see the etcd pods are scheduled to a node in each zone. Now we're going to simulate a zone failure in DAL 10 on these 2 nodes. With the watch on the etcd pods, you will see that the etcd pod starts to go into a terminating state, and then eventually the etcd operator spin back up a new healthy pod in DAL 10. For scenario 2, let's see what happens if all nodes go down in DAL 10. We either have the option to open up a new zone or wait until we can get a healthy node in DAL 10 up. While we are at 2 or 3 pods, the etcd cluster is still healthy and achieves quorum, so there's no outage to the instance. If we were to lose another zone or etcd pod, then quorum would be broken. Back to our Kubernetes cluster, we will demonstrate this scenario. As you can see, we have all the etcd pods back up and running. Next, we will simulate killing all nodes in the zone. With this watch up, you'll see that the etcd pod in DAL 10 goes into a terminating state. As you can see, all the nodes below in DAL 10 have entered a scheduling disabled state and will eventually hit a not ready state. A new etcd pod gets spun up, but will be in a pending state until a new node becomes healthy in DAL 10. Describing the pending pod, you'll see 0 of 12 nodes are available, with 4 nodes unschedulable, and 8 nodes do not meet our pod affinity/anti-affinity rules. For our next scenario, what happens if we break quorum? Quorum is the minimum number of members of an etcd cluster necessary to have it in a functioning state. Quorum is achieved from having majority of pods in a running and healthy state. In our case, it is 2 of 3 running pods. As you can see in this scenario, we lose all of our nodes in Del 10 and a node in Del 12 that has our other etcd pod running on it. With only one etcd pod running, the data is still being persisted in the pod and is in a read-only state to the etcd operator instances. If we were to lose the final pod in Del 12, we will not be able to recover the data, and manual recovery is needed to recover from the most recent backup. Now let's go back to our Kubernetes cluster and demonstrate both of these cases when losing quorum. As you can see, the etcd cluster has 3 of 3 running pods. Now let me write some data to the etcd database. Let's put in kubecon 2020 as the value and demo as the key. Now let me simulate a failure in Del 10 by killing all the nodes in that zone and one node in Del 12. As you can see, 2 of the 3 pods have gone into a terminating state. The third running pod will stay in this running state to allow us to take a backup of the most recent etcd data. Now let's try to read and write to the etcd database again. Let me write the value lost data to the key demo. And as you can see, I'm getting a context deadline exceeded error. Let me try to just read the key demo. And as you can see, I'm getting the same context deadline exceeded error. With this one etcd pod up, let's attempt a backup and restore. So now we need to construct an etcd backup custom resource definition. You can see an example of that here. The sections highlighted in blue is information on where this backup will be stored. It contains the backup location, the path, and the credentials to get to that location. The section highlighted in red is information on how the etcd backup operator can contact the etcd instance. This endpoint is the etcd headless Kubernetes service endpoint for this etcd cluster. Back to the Kubernetes cluster, let's apply the etcd backup resource and wait for it to succeed. You can see that it succeeded by looking at the status field of the etcd backup resource. Now that the etcd data is backed up, we can restore the etcd cluster without losing any of our data. Before we do a restore, let's recover our nodes. Now we need to construct an etcd restore custom resource definition. An example of that can be found here. The section highlighted in blue is the information on where the backup is stored. Notice how this is the same path we used for the etcd backup resource. The section highlighted in red is the name of the etcd backup resource that the data will be copied to. Back to the Kubernetes cluster, now let's apply the etcd restore resource and wait for all the etcd pods to come back up. Now that the pods are back up and running, let's try and read that key from etcd to confirm we did not lose any data. So again, I'm going to read from the key demo. And we can see that kubecon 2020 is still written in that field. Data is still intact and everything is back to functioning normally. For our last scenario, scenario 4, we lose all our etcd pods and break quorum. As you can see here, we lost all our nodes in Del 10, one node in Del 12, and another node in Del 13. Back to the Kubernetes cluster. As you can see, the etcd cluster is back to 3 of 3 pods running. Now let's write data to the etcd database again. Let's put in lost data and write it to the key demo. Let me simulate a complete failure in Del 10 by killing all the nodes, one node in Del 12 and one node in Del 13. Now that you can see all the pods have died, let's attempt to do a backup with the same YAML we used before. As you can see in the status of the backup, we were unable to complete it because the etcd backup operator is not able to contact the etcd cluster. The next step to do is to restore from a most recent backup, the one we saved in the previous scenario. But first, let's recover our nodes again. Now that the nodes are recovered, let's apply the same etcd restore resource again and wait for all the etcd pods to come back up. Now that all the pods are up and running, let's try and read from our etcd database. Let's read the key demo again. And as you can see, the most recent data we wrote, lost data, is no longer there, and it was reverted back to KubeCon 2020. That completes my demo on etcd high availability and disaster recovery.